And can I ask you, brother, to pray for us and open our session tonight?
Yes, no problem. Our Father and our God, the creator of heaven and earth, we thank you once more and again for allowing us to assemble ourselves for this math class. We thank you for our professor as he pours out his knowledge to us that we may be able to receive and grow from the information that we receive. Father God, as our other students are connecting. We just ask that you would be with them also and that everything be well with them. We ask that you would open our eyes, open our ears, open our heart, that we may be able to receive and be able to do well with this class. In Jesus' name, amen.
Amen. Amen. Well, welcome everybody. I hope, hello, brother, and Ruben and Chad. Good to see you all. I hope you had a great Lord's Day. And let's go on for another session. Before we start on a session two, any question you have that you would like me to explain?
I don't have a question, but I did have, I guess, a comment. I think on one of the videos, um, I think it was a long division one or one of those first videos. It didn't want to work. So I don't know if it's just the link's not working, but I tried
Oh,
using it.
okay. Okay, I will check.
Lesson one. Yeah.
Lesson one. Okay, I will check that. All right, thank you for telling me that. Okay. Uh, okay, so if nothing else, let's go. I just want to first go over what we are supposed to do for this week. Let me go to the share screen. Okay, so for this week, we are going to study Blitzer chapter 4, development of ancient, no, development of different system of numeration, and then you have assignment number 3. I mentioned that to Brother Richard tonight. In order to help you with that assignment, I will actually do 2 of the question with you guys, so that you get a sense of what's going on. And not only we talk about the system of numeration, but actually our main emphasis is on what is set and different kind of set, and the diagramming different sets. And so in this week, by Sunday, you're supposed to submit assignment number 3 on Nichols chapter 3 and do the reading summary like before, and then you have quiz number 1. And quiz number 1 is simple. You have to match the item in the first column to the right answer in the second column. So that's about all you have to do for this week. And I was sharing that, don't be overwhelmed. Just go week by week. Let's go week by week, and every week we work with the different problems, assignments, and different concept of mathematics. Okay? All right, so let's go to our PowerPoint. Okay, here. Go in the fit. Before we go to the lesson itself, I wanted to share something that relates to what we discussed last week about the limitation of human knowledge. This is not going to be on any test or quiz, but for your information, and I think it can help you in ministry, because you and I come across people that they believe human knowledge advances as technology advances, and the human can solve all the problems in the world. Now, there's a formula in physics. Heisenberg was a both a physicist and mathematician in early part of 20th century in Germany, and he came with this formula, and it is called Heisenberg uncertainty principle. And basically what it means, this delta sign means change, and this X sign means relates to location, and this letter, which is actually rho, but looks like a P, refers to momentum. And it says the changes in position, time, changes in momentum is greater than or equal to h bar, which is a Planck constant, divided by 2. Now, let me just say a few things before I go to that Heisenberg uncertainty principle. Momentum, or a P or a rho, is basically momentum of an object is its mass times its velocity. So P is a momentum, V is a velocity, M is a mass. And that H, in the Heisenberg uncertainty principle, is a constant, as you can see in this formula. Wait a minute. Okay, energy is H Planck constant times V, or Planck constant speed of light or divided by the wavelength. And sometimes they use a modified form of a Planck constant. Now, all that, let me go back again here. All that it means, what it means is this, that there's this physics formula proves that there's a limit to human knowledge, independent of technology. It doesn't matter what century we are living in or what kind of tools we have. Maybe if I give you a simple explanation, back in the 80s, about 40 years ago, one of the advancements in technology was electronic microscopes. And basically how this electronic microscope worked was you put a specimen under the microscope and you bombard it with electrons, and that will illuminate the specimen, and then you can see that under a microscope. But the thing is this, why you're doing that, why you're bombarding it with electron, you are changing the nature and the fabric of that specimen. So you're not really seeing what it was in reality, in nature. You are seeing a distorted version of it. And no matter how advanced your tool becomes, it doesn't matter. There's a limit that it cannot change. This formula says, in other words, let me, again, another example. If you see a pen in my hand, if you want to measure, if this pen is keep moving, you can either increase your knowledge of its position, but if you do that, the momentum, your knowledge of its momentum goes down, because this relationship must stay constant. And this h bar is a constant. It doesn't changes whether I'm using electronic microscope, laser microscope, or whatever. It always remains the same. So you can either increase your knowledge of the position of my pen, or you can increase your knowledge of the momentum of this pen, but you cannot increase both of them at the same time. When you increase one, you lose the other. You increase this one, the other must go down, in order that this constant, this rule must hold. So that means no matter what kind of advanced technological tool we use, there is always limit to our knowledge. There's nothing we can do except that we must trust the revelation from the creator of this universe. Okay, this is I use that sometimes in response to people who deny the existence of God and say man can, reaches the apex of knowledge by technology advancement in science, there's a limit. There's a limit. We are in a box and we cannot go outside the box. The only way we can know about outside the box are the revelation that comes from the creator from outside the box. I hope I didn't confuse you, but basically this Heisenberg uncertainty principle proves that there's a limit to human knowledge, no matter what's the status of technology. And Planck constant, in other words, is in physics we have quantum mechanics that says energy is exchanged in a specific amount or quanta, and Planck constant define how much energy are in those quanta. Again, but these things it's just for your own knowledge. They are not going to be on any test or quiz. Okay? Any question? If not, we can continue.
No, I do have a comment though. I think what you're saying is, I agree. What are your thoughts regarding AI now that that's becoming very popular with artificial intelligence? And you talk about technology, but I know there's limitations to the human aspect of it. But like, it seems like people are leaning more to AI the more and more time goes by.
But you see, AI is basically operates based on what human tells to AI what to do. AI cannot make decision independently from the human that gives the AI, whatever AI that we have. It cannot make decision independent of the humans. It just can operate faster, and it can relate to different things much faster and combine things together. But in other words, it does not have. Oh, I'm sorry. My cat created a problem. It does not have a self-conscious. And it cannot become self-aware. That's stories of science fiction, but it doesn't have consciousness, and it cannot become self-aware of itself. It just does what we tell him to do. Okay. All right. So let's continue. We are going to talk tonight about sets. So we can have different sets of different things: butterfly, vehicles, boats, fish, animals. Basically, a set is a collection of objects, those objects are members or elements of that set. A set is well defined. Now, this is one of the questions on the assignment. When the contents can be clearly determined, when we can know the elements in a clear sense. Now, there are three ways to indicate a set. You can describe it, you can use a roster form, which we'll talk about it, or you can use a set builder notation. Let's talk about it. First, about description of a set. For example, the problem is write a description of the set containing the elements of Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. Answer: this is describing the set. The set is a days of the week. That's it. And then listing the elements of the set. We want to put it in a roster form. We use a pair of braces, not parentheses, and not brackets, but a braces, and then we put the elements within that between those braces, and so we separate them by a comma. For example, we can have this set here, 1, 2, 3 is a roster form. This is a roster form notation for a set, and the elements are, its members are 1, 2, and 3. But this form, the using a parenthesis or a brackets, they are not the set. They're not set because parentheses and brackets do not indicate a set. And then we can name a set with a capital letter. For example, if we have a set of natural numbers, the common letter that is used is capital N. Or natural numbers are counting numbers. Natural numbers, you see, as you can see here, we call it a name with capital N, and then we use braces, and we put 1, 2, 3, 4, 5, and there's 3 dots called ellipses. It means that it continues. They're positive numbers, positive integers. Natural numbers are positive whole numbers for counting, such as 1, 2, 3, and so on, up to infinity. Okay?
You said you mentioned the type of brackets that go around the sets. Is it the parentheses or I see
No. It has to be braces.
Braces, okay.
Not brackets and not parentheses. That tells us this is a set. Okay?
Mm-hmm.
All right, so I go on, and now, so we talked about description of a set. We talked about the roster form of a set. So let's look at some example for you here. It says, express the following in a roster form. A set A is a set of natural numbers less than 5. So here is the answer. A is a roster form would be capital A equal to 2 braces, natural number, meaning number, counting number like 1, 2, 3, 4, 5, 6, and it says less than 5, so it's only 1, 2, 3, 3 and 4. That is set A. You follow me? Okay. Now, set B is a set of natural numbers less than or equal to 75. Now, you see, when it says less than or equal, it means it includes 75. I start with B 1, 2, 3, 4, then I don't have to write all the numbers to 75. I put 3 dots, and then I include 75. And that because it says less than and or equal, so it includes number 75. All right?
The comma after the 4, and then you have the comma.
It means that the next number would be 5, 6, 7, 8, 9, 10, all the way to 75. But just, we don't want to write all those numbers.
Yeah, the ellipse.
So we put a comma, 3 dots, comma, 75.
Okay.
Or set P is a set of planets in Earth's solar system. So we call it P equal to, again, 2 braces, and then we put the planets, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Plato used to be, but I guess astronomers decided to cancel that as a planet. All right?
I have a quick question. On
Sure.
set B, I understand everything you're saying there. Could we do up to 3 and then do the ellipsis and go all the way to 75?
Sure.
Or
Yeah.
yeah. Okay.
You can do that too.
Okay.
Then, here it's important to remember 2 words when we use the word between and when we use the word inclusive in the roster form of a set. For example, if it says write a set of natural numbers between 4 and 9, it means you don't want to include 4 and 9. You go what's between them, 5, 6, 7, and 8. Now, if it says, a set of natural numbers between 4 and 9, but write it inclusive, meaning include numbers 4 and 9, then we write 4, 5, 6, 7, 8, and 9. This is an inclusive set. It includes the values of 4 and 9. Okay? So let's continue. Now, another thing is set builder. Or set generator, set generator notation. That can also be used to symbolize a set and is frequently used in algebra. Now, when we have this symbol that looks like E, capital E, but it's not really E, that symbol means this element it's an element of what that set. For example, if I have a set A, and I have 5, 6, 7, and 8, we can say 6 is an element. When I use this symbol, it's element of A, because 6 is part of this set, 5, 6, 7, and 8. We may also write 9 is not, we put a cross, a line cross that symbol, is not part of A, because 9 is not an element or a member of set A. Okay? Following me? All right. Let's go on. So, if we want to express a set in a set builder notation, this is it. We put two braces and we say all X such that, let me move this thing. Such that X is equal or less than or equal to 2. All the number that's less than or equal to 2. But again, you probably get more description. It's a natural number or a real number or whatever. But that set formation, if you want to read it, is a set of all X such that X is less than or equal to 2. Okay. We move on. Again, like here, for example, when it says, X is less than A, then it says set of X such that X is a natural number and is less than 4. So, in that case, the set would be only 1, 2, and 3. Following me? Okay. And if we have second one, it says less than or equal to A. Again, X is a natural number less than or equal to 4. So, because it says less than or equal, now we include 4 also in our set. Or it can say X is greater than A. Then you write set of X such that X is a natural number and X is greater than 4. So you don't include 4, you go 5, 6, 7, 8, then 3 dots all the way to infinity. Okay? Let me do, for example, let's do this one. If it says X greater than equal to A and less than or equal to B. So we have a set X of such that all the X such that X is a natural number, and then we put a value for A and B as 4 and 8. So it's greater than or equal to 4, but it's less than or equal to 8. So it includes 4 and 8 and the 5, 6, and 7 that are natural numbers between them. You see that? But in the next one, when it says just less than B, then you don't include 8. Or in this one, just says greater than A, then you don't include 4. Following me? Okay. So we continue. Now, what's a cardinal number? Cardinal number is a number of the elements, number of members of a set. And we usually use the symbol n parenthesis a or n of a. So cardinal number answer the question, how many? How many members are in a set? Let's look at, for example, example 8 on page 50. Okay, example 8, in the middle of page 50, it says, if it says set A has, these are its members, 7, 9, 11, and 13. What is its cardinal number? How many members are in it? 7, 9, 11, and 13, 4. So the answer is 4. Set B, it says it's a set that has only 0. 0 is a number. Don't forget, don't make that mistake. So the cardinal number for B is 1. But set D, you see that symbol circle with a line across it, it means null, empty. So that one, the cardinal number is 0. And C, when it says a set, it goes from 13 to 23, it basically number 13, 14, 15, all the way to 23. There are 11 numbers. So the cardinal number is 11. So remember, the cardinal number answered the question, how many? How many members are in that set? Now we have finite and infinite set. Now, please don't confuse the cardinal number with whether a set is a finite or infinite. In other words, set A is a finite set if the cardinal number, either 0, that is A is the empty set, or it has no member, or n of A. So A is a natural number. Now remember, I know natural numbers are infinite, but we are not talking about a set of natural number. We are talking about the cardinal, how many members are in a set. If a set whose cardinal is not a 0 or a natural number is considered an infinite set. For example, if we have here a set of natural number, it goes 1, 2, 3, 4, 5, 6, all the way to infinity. This is an infinite set. Okay? And a universal set is all the elements, members of any group, put them together. And usually when we want to assign a cardinal number, if a cardinal number is infinite, that's how we assign it. We write x or chi 0, aleph null, aleph from the Hebrew alphabet, and 0 means null. It means it has the cardinal number is infinite. The cardinal number of a set of natural number is infinite, for example. All right. I know it can be confusing, but when you practice, if you read the chapter, do the examples, you will get it. Yes, you know, it's mathematics is like any language. You have to practice to learn it.
Okay.
All right, let's move on. Now, equality of a set. Set A is equal to set B. That means that they have exactly the same elements, regardless of their order or repetition. When they have the same elements, they are equal. And we write them A equal to B. For example, if set A is W, X, Y, Z, and set B is Z, Y, W, X, they are equal because they have exactly the same elements, even though their order or the order that the elements are written, they are different. For example, if you look at example 10 on page 53, it gives you set F489 is equal to the set which is 894. That's a true statement. But in example B, it says 135, and the other set is 0135. No, they are not equal, because the first set doesn't have the 0 number. All right, let's continue. Now, we talked about subset, and we have two different kinds of subset. Just a regular subset and a proper subset. Set A is a subset of set B, and we use this symbol with a bar at the end, if and only all the elements of set A are also in the elements of set B. This little bar means equality. But set A is not a subset of set B, then we don't put that bar, and we make a cross, a line cross that symbol. Let's look at page 57, for example, example 1. It says in A, it says set A is 1357, set B is 1357, 9, and 11. You can say here, you see, here's the thing. You can say set A is a subset of set B. Actually, I disagree with the way that they put a symbol down here. They shouldn't put the equal bar, because they don't have exactly the same number. It is actually, this is what is called proper subset. But let's look at example B. It says A is X, X is a letter of the word proof, and B is Y, Y is a letter of word roof. They are not equal, because they cannot be subset, because set A doesn't have, set B doesn't have the letter P. Okay, you follow me?
Which one were you on that one?
I would say, in the book it says, yes, it is not subset and equal, but it can be a proper subset, because set B has all the, all the elements in set B are in set A. So I can say B, now, instead of the way that it's written, I can say B is a subset, a proper subset of B, of A. It would be here. We are talking about proper subset. If you, in the PowerPoint, you see, if set A is a subset of, but not equal to B, such as the example that you have here, B is RO and F, A is PRO and F. They are not equal, but all the elements of B are in set A, then you can say it is a proper subset. And we can use this, we use this symbol without the bar. All right. Let's look at, for example, example 59. Example 59, example 2 on page 59. It says set A is X. All the X is a person. X is a person, and X lives in San Francisco, and B, X is all the person living state of California. Okay. This is a proper subset, because all the people who live in San Francisco also live in California, but all the people in San Francisco doesn't include all the people of California. So it should be Yes, if you can see it, it should be the second notion. Is A is just a member subset of B, proper subset. You follow me? Or look at example B. Every member in A is 2468. It's contained in B 2468. Now you can say it's a subset with an equal sign. All right? Are you guys okay?
When it went down, okay, you're on number 2 right now, correct? Okay, so it says both in each blank to form the true statement. So A equals 2468, and then B 246 and 10. So 8 is left out. So it's not.
Okay, yeah, you're talking about the checkpoint number 2. We're not talking about example number 2. Yeah, so you can say A is a proper subset of B. You can use this symbol, this one, not this one, because they're not equal.
Okay.
Follow me?
Yeah, that the equal sign with the slash in it.
Yeah, no. Just don't use this one. Just this kind of inverted U.
Okay. Okay, I
Because
see.
it can be,
but not with the line under it.
No, not with the line.
Okay.
Because it is a proper subset.
Okay.
What about on the one you were just talking about on that B?
On the B, example B,
Yeah.
it should be with the inverted U with the equal sign because the members are the same.
Okay, so that one does have the one in the bottom because it has all the same elements basically.
Yeah.
Okay.
All right. The symbol used.
Can you go? I'm sorry. Can you go over the first one again? The example 2, the A with California and San Francisco.
Okay. You see here, I differ from the textbook. I say the only proper answer to that would be the second answer. A is a proper subset. That subset symbol without the equal bar. Because all the people in San Francisco are in California, but all the people in San Francisco doesn't represent everybody in California. San Francisco is a part of California.
So it would just be the C symbol.
Yeah, it would be, or a C symbol.
Gotcha.
Okay. Okay. Let's move on. So when it says, it's good that you can call it a C. When you have a C with a bar, it's a subset. When we have a C with no bar, it's a proper subset. Okay? So, subset for a set A and B. Set A is a subset of set B. If every element in set A is also in set B, then we have that C with the equal bar. Proper subset is for set A and B. Set A is a proper subset of set B if every element in set A, they are also in set B, but they are not equal. So it's just the C or an inverted U. All right. So let's go on. And we have what is called an empty set. But this empty set is a subset of every set. Emptiness can be part of everything. And it's usually marked with a 0 and a line across it. It's called null. Furthermore, the empty set is a proper subset of every set except itself. So, for example, if set B and B is an empty set, then for any set B, or I'm sorry, let me rephrase it. For any set B, an empty set is a subset of it. And for any set other than the empty set, again, we can write is empty set is proper subset of B when B is not the empty set itself. All right. So let's move on. Okay. So we have another thing that we have when we diagram, we have what is called, let me get this thing out of here, a complement of set A. If this is set A, the complement would be this purple area, which is called A prime. You know, you can use this thing, this diagramming is useful in church study when you want to study your congregation. What are the percentage of the elementary students, middle schools, high school, college age, married, single? You can use these diagrams. If you have a set A, its complement is A prime that fills, in a way, fills the universe. Okay. Then we can have intersections of different sets. If I have three sets, A, B, and C, then we have intersection of A and B is this yellow area. Intersection of A and C, we put with this inverted U, it's this area, purple area. Intersection of B and C are these. Intersection of all three of them is this white area. A, B, and C. All right. It's very simple. We'll see an example. Their union is when it's a set that combines all the elements in both set A and set B. Union of AB, or it's equal to union BA, and that's a union operation. You put all the members together. And there's something which is called Venn diagram. Again, let me see. Venn diagram is a widely used diagram style, shows the logical relationship between sets. It was popularized by a mathematician, John Venn, in 1880s. For example, this, yes? Okay, we have set A, set B, and set C. Set A contains A, D, G, and E. Set B contains B, D, G, and F. Set C contains C, E, G, and F. G is the only element that is in all three of them. Okay, and outside there's none. Let's move on. Let's watch. This thing explain it in a very good way. The use of Venn diagram.
Is it supposed to be sound to
Yeah.
it?
Can anyone else hear it?
No.
Yeah, I cannot.
Are you okay?
No sound.
Yeah, no sound.
No sound?
No sound.
Oh, boy. Ah. I don't know. Okay, let's maybe watch it from here. Do you hear? Do you hear the sound?
No sound.
No sound?
No.
Nope, no sound.
You still don't hear anything? Oh, boy. Well, I don't know what's the problem. Just let me go back here. Just one moment. Uh, let's try again. Otherwise, if you still can't hear, you can hear me, can you?
Yes.
Okay. If you cannot hear the video, there isn't much saying, you're just playing music. So let me go on. Can you hear anything?
No.
Okay, I'm sorry, I don't know.
It's okay.
Yellow. Smooth.
Now we fear it.
Oh, you can hear?
Fruit. Yellow.
Yeah.
Okay.
Oh, but it went out again.
Yellow.
Okay, if you still couldn't hear on the Populi, if you go to session 2 and go over the PowerPoint, when you reach there, you can click and you can hear it on your own computer. You didn't hear anything?
No.
Okay, sorry about that. I don't know what's wrong. Okay, now let's consider these two sets and consider each friend as an element. We have one set that people play soccer and one that people play tennis. We have Alex and Casey, Drew and Hunter, Casey, Drew and Jake. All right. So if we want to do a Venn diagramming, if we want to use a union of soccer and tennis sets, would be all of them. So we put these braces, and it would be Alec, Casey, Drew, Hunter, and Jake, because it includes both sets. Okay? If we want intersection, meaning people who play both soccer and tennis, would be only Casey and Drew, as you can see in this purple area. And if we want the set that plays soccer, but they don't play tennis, we want people that only play soccer, would be only Alex and Hunter. Okay, so it's only that purple area. Or, so union means either set. It can be in either of the set. Intersection means it must be in both set. The difference is means it in one set, but not the other one. All right. So let's say the third set is volleyball, which has Drew, Glenn, and Jade. So volleyball is a set that has, again, two braces, Drew, Glenn, and Jade. S is a soccer set, T is a tennis set, and V is a volleyball set. So if we want to have the union of them, it would be all of them. All the members in set S, set T, and set V. It includes everybody. It includes people who play soccer, tennis, and volleyball. And when you notice, there's no one who plays only plays only tennis. This part is empty. Or Alex and Hunter, they play soccer, but they don't play tennis. Jade here plays tennis and volleyball, but doesn't play soccer. Okay. All right. Set S is the only people who play soccer is Alex, Casey, Hunter, and Drew. Union of set people who play tennis and volleyball would be these guys, Casey, Drew, Jade, and Glenn. The intersection, meaning a person who plays all these three games, it has only one person, and that's Drew. And what's the empty set? This is the intersection of set S and V minus set T. So if you want to write it, would be intersection of set S and V without T. So that's an empty set. And you write it this way. And it's empty, and actually you have to put that null sign in the braces. Okay, you're following me? All right. So universal set would be all the people who play soccer, tennis, and volleyball, and people who are outside of these three games. It includes Blair, Erin, Francis, and Ira. So, but if everyone who does not play soccer, then you take S and you take a union minus S. So it's all the people who are in the purple color. All right. So Alex, Hunter, Casey, and Drew are pulled out. You follow me? All right.
Mm-hmm.
Then everything that is not S means outside of S. So you have again a purple area. And it's written as S prime because that's a complement of set S. Let's look at page 68. Example 3. It says if set U is number 1 through 9 and set A is 1, 3, 4, and 7, find A prime. Okay? Set U is our universal set. So we must choose within that set. A prime means not A. So whatever it's not A, well, A has 1, 3, 4, and 7. So you go to set U, universal set, and cross 1, 3, 4, and 7. So you end up with 2, 5, 6, 8, and 9. That is A prime, or not A. Okay? All right? You follow me? Okay, let's move on. What are sets are important? Well, basically, they allow us to use collection of objects, mathematical object, as an object itself is a starting point of, you see, as I mentioned always, mathematics is like a language, and the starting point for understanding mathematics, you got to know definitions. And without set, we have a difficult time to give definition of mathematical object, to define mathematical object. So definition relying on sets. Here we come to what is called a function. A function is a rule that maps number to other numbers. But again, it's a question of what's a rule. It can be vague. For example, if I have 2x and then I have 2x plus 1 minus 1, there are different rules in these two functions, even though the final result, the output, are the same. Because plus 1 and minus 1 cancels, and 2x is always 2x. So we define a function as a set of ordered pairs. Let me show you. Okay, just be patient. We will see. In chapter 6, we haven't got there yet. We'll address domain of function, where a function gets its input and maps numbers to numbers. And then you see the thing that does that mapping is the operators. But again, we cannot really pin down what things means unless we have a mathematical notion. That's where the need for set comes from. Let me show you, for example, here, function and non-function. A function can be one-to-one. For example, there's an operation that takes a to x, whatever that operation. And we are not talking about, we are not looking at what operation, but there is an operation that takes a to x, b to y, and c to z. That's one-to-one. Or it can take a and b to x and c to z. So it's a many-to-one. But the other one, they are not function. You cannot take one element or one object to two different numbers. In other words, let me give you an example. 2x, if I assign a number to x, let's say x is 3. 2x always give you what? 6. It cannot give you 7. It cannot give you 8. If we try to do that, we don't have a function. We don't have a proper operation. So it cannot go from one element to two. This is not, even though on another occasion it can take one-to-one, but this is one to many. This is not a function. Or B cannot go to two different numbers, or C to two different elements, even though one of it can. So remember, to have a function, it must always go from one to one, or from two elements to one, but it cannot go from its domain. This is a domain, cannot go to, A cannot go to both X and Y. It cannot go to two different numbers. If 2 times 3 is always 6, you cannot have 2 times 3, 6, and sometimes 2 times 3, 8. All right? Let's, again, okay. I hope you can hear this. Otherwise, right. Well, let me try, then tell me, can you hear it or not?
A function, and I'm going to speak about it in
Yes.
abstract
We
terms,
can
You
hear
right?
it.
Is
Oh,
something
thank
that
God.
will take an input. It will take an input and it'll munch on that input. It'll look at that input. It'll do something to that input. And based on what that input is, it will produce a given output. So what is an example of a function? So I could have something like f of x, and x tends to be the variable most used for an input into the function, and the name of a function tends to be the most used variable, but we'll see that you can use others. But we could have f of x is equal to, let's say, x squared if x is even, and let's say it is equal to x plus 5 if x is odd. So what would happen if we input 2 into this function? And the way that we would denote inputting 2 is that we would want to evaluate f of 2. This is saying let's input 2 into our function f. And everywhere we see this x here, this variable, you can kind of use as a placeholder, let's replace it with our input. So let's see, if 2 is even, do 2 squared. If 2 is odd, do 2 plus 5. Well, 2 is even, so we're going to do 2 squared. So in this case, f of 2 is going to be 2 squared, or 4. Now, what would f of 3 be? Well, once again, everywhere we see this variable, we'll replace it with our input. We'll replace it with our input. So f of 3. So 3 squared if 3 is even, 3 plus 5 if 3 is odd. Well, 3 is odd, so it's going to be 3 plus 5. It is going to be equal to 8. Now, you might say, okay, that's neat, Sal. This was kind of an interesting way to define a function, a way to kind of munch on these numbers. But, I could have done this with traditional equations in some way, especially if you allowed me to use the squirrely bracket thing. What can a function do that maybe my traditional toolkits might have not been as expressive about? Well, you could even do a function like this. You could have, and let me not use f and x anymore, just to show you that the notation is more general than that. So I could say h of a is equal to the next largest number that starts with the same letter as variable a. Says as variable a, and we're going to assume that we are dealing in English. So given that, what is h of 2 going to be? Well, 2 starts with a t. What's the next largest number that starts with a t? Well, it's going to be equal to 3. Now, what would h of, I don't know, let's think about this. What would h of 8 be equal to? Well, 8 starts with an E. The next largest number that starts with an E, so it's not 9, 10, it would be 11. And so now you see it's a very, very, very general tool. This function is this H function that we just defined. We'll look at it. We'll look at the letter that the number starts with in English, and so it's doing this really, 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 really wacky thing. Now, not all functions have to be this wacky. In fact, you have already been dealing with functions. You have seen things like y is equal to x plus 1. This can be viewed as a function. We could write this as y is a function of x, which is equal to x plus 1. If you give as an input, so let me write it this way. So for example, when x is 0, we could say f of 0 is equal to, well, you take 0, you add 1, it's equal to 1. F of 2 is equal to 2. You've already done this before. You've done things where you said, look, let me make a table of x. Let me take and put our y's there. When x is 0, y is 1. When x is 2, I'm sorry, this was when x is, mistake, where f of 2 is equal to 3. And you've done this before with tables where you say, look, x and y. When x is 0, y is 1. When x is 2, y is 3. So this, you might say, well, what was the whole point of using the function notation here to say f of x is equal to x plus 1? And the whole point is to think in these more general terms. For something like this, you didn't really have to introduce function notations, but it doesn't hurt to introduce function notations because it makes it very clear that a function takes an input, takes my x, and in this definition, it munches on it. It says, okay, x plus 1, and then it produces one more than it. So here, whatever the input is, the output is one more than that original function. Now I know what you're asking. All right, well, what is not a function then? Well, remember, we said a function is something that takes an input and produces only one possible output for that given input. So for example, something like, and let me look at a visual way of thinking about a function this time, or a relationship, I should say. So let's say that's our y-axis, and this right over here is our x-axis. And let me draw a circle here that has radius, let me draw a circle here that has radius 2. So it's a circle of radius 2. This is -2, this is +2, this is -2. So my circle, it's centered at the origin. It has radius 2, so that's my best attempt at drawing the circle. Fill it in. So this is a circle. The equation of a circle, of this circle, is going to be x squared plus y squared is equal to the radius squared, is equal to 2 squared, or it's equal to 4. So the question is this relationship between x and y, here I've expressed it as equation, here I've visually drawn all of the x's and y's that satisfy this equation, is this relationship between x and y a function? And we can see visually that it's not going to be a function. You pick a given x, let's say x is equal to 1. Let's say x is equal to 1. There's two possible y's that are associated with it. This y up here and this y down here. We can even solve for that by looking at the equation. When x is equal to 1, we get 1 squared plus y squared is equal to 4. 1 plus y is equal to y squared is equal to 4. Or, subtracting 1 from both sides, y squared is equal to 3, or y is equal to the positive or the negative square root of 3. This right over here is the positive square root of 3, and this right over here is the negative square root of 3. So this situation, this relationship, where I inputted a 1 into my little box here, and associated with the 1, I associate both a positive square root of 3 and a negative square root of 3. This is not a function. I cannot associate with my input two different outputs. I can only have one output for a given input.
Okay. I hope this makes sense and explain.
Function.
Okay. Explain things. All right. Now let's move on the definition relying on sets. Algebraic structure or topological spaces are considered as a set with operation on them. The whole power of modern algebra is that it can be applied to set of anything, okay? And we will see that in our exercises, assignment, and examples. Now, we come to chapter 4 about number presentation and calculation. Now, again, don't be afraid. I'm not expecting you guys to memorize like a Roman numeral or Hebrew numeral or what a Mayan numeral. But, basically, set of numeration has a set of basic numerals and rules for combining them to represent number. It is very important, like in a number system that we have, Hindu-Arabic system, it's a place value. Actually, all of them are place value or positional value. It means that depending on where the digit is, its value changes. The value of symbol depends on its position. For example, when you have number 20, the 2 in the 20 is in tens. The 0 is in a position one position. The 2 in a number 200, it represents 200s. Okay? A true positional value system requires a base set of symbols and also includes symbol for 0 and 1 for counting. And the most common positional system is the one that we use, the base 10, and which is also called decimal number system. Okay. Oops. For Hindu-Arabic numeration, which you see you have numbers start from 0, it goes all the way, and these are called digits. Then from 1 to 12, they have unique names. Then from 13 to 19, we add teens. And then it goes on, numbers from 20 to 99. The 10th place is named first. Numbers 100 through 199, 999 are combination of hundreds and previous names. These are just examples. I mean, this is obvious. You all know that. We have another numeration system. It's called exponential numeration system. And in exponential notation, you have a base, and then you see have a b to power of n. B to power of n means b appears n times. This is exponential expression. For example, b to power of 1 is b to power of 0 is 1. Any number to power of 0 is 1. The nth power, or oops. Let's look at page 195, checkpoint 1, page 195. Okay, page 195, example 1 at the top of the page. For example, you have 10 to power of 2 means 10 times 10, 100. 10 to power of 3 means 10 times 10, 10 times 10. And it goes on, 10 to power of 4. 2 to power of 6 means you multiply 2 6 times. And 1 to power of 7 is 1. 7 to power of 1 is 7. Okay? It's simple, nothing complex here. But just remember that the number, like a 10 to power of 2, 10 is the base, and the 2 is the exponent or power. All right. This is very important in all numerical system, and it's a positional value. And we start from the right-hand side here. It's 1, 10, 10 to power of 2, 10 to power of 3, 10 to power of 4, it goes on. To evaluate a numeral in the Hindu-Arabic system, we multiply the first digit on the right by 1, and then by 10, then by 100, then by 1,000, and it goes on. For example, when you have 572, and if a question asks you to expand that, just do this. Write each digit 5, 7, and 2. Then start from here. Start from right-hand side. This is, we are using base 10, and it's in the first position. Remember now the formula. I will show you the formula. The formula is this. You go based on the position minus 1. This is the first position, okay? So 1 minus 1 is 0. Any number to power of 0 is what? 1. So you get 2 times 1. Now here, 7 times, we are in the second position. So we have, so we have second position, and it's 2 minus 1 is 1. So we have 10 to power of 1. We have 10. Now we come here to the third position. It's again, it's base 10. It's a third position minus 1, so it becomes 2. 10 to the power of 2 is 100. So it becomes 500 plus 70 plus 2, 572. Follow me?
Can you explain that again? You said start on the right.
Okay, yeah. Let's say example is write 572, expand that. And we are using base 10 positional system. So we want to expand that. So what you do is take each of the digits, 5, 7, and 2, and write it 5, 7, and 2, okay? Plus, plus. Then you start from here, start from the right-hand side. This is the first position. Let's call the position n. The formula is this, n minus 1. 1 minus 1 is 0. Okay, so any number to the power of 0 is 1. That's why you end up with a 1 here. Okay? Now look at the second one. This is a second position. N is 2. The formula is n minus 1, so you get 1. So you have 10 to the power of 1. Where does that 10 come from? We are using a base 10 numerical system. And you come here. This is a third position. So n is 3. N minus 1 is 2, so you have 10 to the power of 2, 100. And when you multiply them by those digits, you get 570 plus 2, or 572. Okay? Are you okay, Richard?
Trying to.
So just take the number, put the digits, and then start from the right-hand side. That's the first position. And the formula, maybe if I show you here, makes it much easier to understand. The formula is this, when we are using base 10, 10 to the power n minus 1. Okay, so when you have n minus 1, it means when I come here, the first case that I have is 1 minus 1, which is 0. 10 to the power of 0 is 1. Okay?
Okay.
And it goes like the second position, n is 2. So you have 2 minus 1, 1, 10 to the power of 1. Third position is n is 3. 3 minus 1 is 2. So you get 100. Follow me? Are you okay, Richard?
You continue. Go ahead.
Okay, all right.
Yeah, because I don't want to hold us
No,
back.
that's okay. So we multiply the digit n places from the right by 10 to the power of n minus 1. Therefore, for example, we multiply the digit 8th place. If you have a digit that is in the 8th position, we multiply it by 10 to the power of 8 minus 1, 7, or 10 to the power of 7. Using the place value rules, we can write a number in an expanded form. For example, if it was asked, write 1234 in an expanded form, that's the way this is what you do. You take 1, 2, 3, 4. Okay, open 3 parentheses. Put each of these digits 1, 2, 3, 4. 4, 3, 2, 1. Okay. This is a first position. So you have n minus 1. 1 minus 1 is 0. So this becomes 1. Any 10 to the power of 0 is 1. It's a base 10 numerical system. All right. The second position, it's n is 2. 2 minus 1 is 1. So you have 3 times 10. All right. The third position, and we are in the third position, n is 3. So n minus 1 is 2, and you get 100. The fourth position, n is 4. 4 minus 1 is 3, so you get 1000. And that's when you add them together, you get 1,234. All right. So Babylonian numeration system, we have Mayan numeration system. Babylonian, its base of 60 is called sexagesimal system, and not a true place value system, as it had no value, no symbol for zero, and that's why these numerical system died out. The positional value was like this. Again, the rule continues, the same rule of b to power of n minus 1. So you get, if it's a first position, you get 1 minus 1, 0. Any number to power of 0 is 1. But here, remember, it's a base 60. So it's 60 to power of 1, then 60 to power of 2, and 60 to power of 3, and so forth. So remember, you're working on what's the base of that numeration system. Let's look at examples 4 and 5, page 197, 198. For example, it talks about page 197, the Babylonian numerical system. It asks us to convert them, Babylonian numeral to the Hindu Arabic symbol, example 4. And it gives you the table. Nobody expects you to memorize these tables. It will be given to you. And for example, look at the first one, A. It gives you it has all the symbols and says write that in a Hindu Arabic system, which is base 10. And in that table, we have, when is that little v is 1, and the kind of a fallen v is 10. And we have these things. We have 2 v's and fallen v, and a v, 2 fallen v, and 2 v's. So, okay, we look at the table. We see v is corresponding to number 1 in our numerical system. So we start from the right-hand side. We have place value 1. We have any number to power of, even though it's a base 60, but because it's first position, and so n minus 1 is 0, so it becomes 1 times that parenthesis. Now, inside the parenthesis, 2 of those inverted v, each of them has a value of 10. So we have 10 plus 10, and those correct v are value of 1. So we have 1 plus 1. Okay, you follow me? The second digit, it's inverted v and a regular v. Okay, so it's, first of all, we are in the second position, so it has to be 2 minus 1, so it's base 60, so we have 60 to power of 1, and then we have the inverted v is 10, and the regular v is 1, so we have 10 plus 1 times 60. And then the third position, again, third position, number 3 minus 1 is 2, it's base 60, and then we have 2 regular v, each of them is 1, so we have 1 plus 1. And then you just add them and multiply by that whatever base that you have. So that symbol, that numerical symbol in Babylonian numerical system is equivalent to 7,882 in our Hindu Arabic numeral system. All right, you follow? So that table will be given to you. All right. Or let's look at page 198 also. Okay, that's, I'm going a little bit forward ahead of myself, but this talks about the Mayan numeration system, and it gives you table 4.2. And then, for example, look at example number 5. And they have some rules for themselves, arbitrary. I mean, they just set these rules. Why they set it, maybe depending on their calendar. So in the Mayan system, the first position, again, it's a base 20, but the first position, okay, is again 1 minus 1, 0 is 1. You multiply by 1. The second position, you multiply by 20. The third position, the base is 1820. You multiply by 1820. That's the way they form their numerical system, probably based upon their calendar. There's no other reason for it. For example, let's look at example 5 and do number A. Example 5, number A on page 199. If you have that Mayan numeral and you always start from the bottom, you go up. When you have 2 bars and 2 0, that is equal to 12 from the table 4.2. The second symbol equals to 7, the third symbol equals to 0, and the fourth symbol at the top, it's vertical, we go from bottom to the top, it's 14. The one at the bottom is a position 1, then position 2, position 3, position 4. So we multiply. First position, it becomes 1, so 12 times 1. Second position, we multiply by 20. Third position, 1820. The fourth position is 18 times 20 to the power of 2. I'm sorry, 20. My eyes can see. Let me put my glasses. Yeah, 18 times 18 to power of 18 times 20 to power of 2, the fourth position. Yep. Okay. Now, there is a question in assignment 3. I will do that together today, so you follow me. And I'm not expecting you to memorize these tables, and the assignment and quizzes are much, much simpler than what you think. And in fact, there is no test. There's no question on the test or quizzes asking you about Babylonian, doing this. Please study them for assignment, but don't worry too much about it. Babylonian system is base 60. A place value system with a base 60. We talked about that positional value. We went over this. This is Mayan system. For example, here I have simplified the numbers. Again, when we have this number starting from bottom to the top, the 2 bar is it's the first position, so it's the 2 bar is number 10 from the table 4.2. Okay. This oval shape look like a ball is 0. Just a dot is 1, and 2 dots and 2 bar is number 12. Okay, so you write that 12, 1, 10, 0, 10, and then multiply. This is the first position, so it always becomes 1. The second position we multiply by 20. The third position it's 18 times 20 to the power of 2. I simplified that, made it 20, so it becomes 400. The fourth position is multiplied by 8,000. It's 18 times 20 to the power of 3. I made that 18 to 20 to simplify the numbers. So you multiply 96,000 plus 400 plus 0 plus 10, and then you add them. So that Mayan numeric number is equivalent to our 96,410. Following me? Okay. And we already did that, I believe so. Yeah. The Greek numbers, again, they have Greek alphabet and they assign numbers to it. This is Roman numerals. We use some of the Roman numerals, but not all of them. For example, 154 is equivalent to CLIV, but 1492 is that massive number. 3,495 is that other math. I just imagine trying to add or multiply. That's the reason this numerical system died out, because they couldn't work. It's impossible. Just think of trying to multiply these numbers. Hebrew system, again, they have their alphabet and they have numbers assigned to the alphabet. It doesn't have a base because they are not a positional numerical system any more than Roman numeral. For example, if you look at number 764, if you want to find 764 in Hebrew, is that starting from right to left. It would be Ta Sin O Dalet. So it would be, if going there, the Ta is here, 400. The Sin is here, or Shin actually, 300. The O is 10 right here. No. What is it? Or here, 60. Actually, it's this one. This one. And Dalet is 4. So you put them together and you get 4 plus 60 plus 300 plus 400, which is 764. All right. Just know this for your knowledge. Okay. Don't worry about it. Don't be scared about that. All right. Basically, number-basing positional system is you have, you can have different bases. Our number system is base 10. And then we go like this. B to power 4, position number 4, position 3, position 2, position 1, position 0. Or actually, I'm sorry, position 1, position 2, position 3, position 4, position 5. For example, if you have a numerical system that is a base 8, you will end up with 1, 8, 8 to power of 2, 8 to power of 3, 8 to power of 4. Or if your system is base 2, you get these things. When a base is 2, it's called binary. When its base is 8, it's called octal. When base is 16, it's called hexadecimal. All right. Converting, and again, don't worry, I'm not asking you to do multiplication on other base system, but if we have a number which is base 6 and we want to convert that to our own numerical system, base 10, this is what we do. Again, write the digits 4, 5, and 3. 4, 5, and 3. Put parentheses around that. This is first position. B to power, B is n minus 1. 1 minus 1 is 0. Any number to power of 0 is 1. This is the second position, and it's base 6. So n is 2. 2 minus 1 is 1, so 6 to power of 1 is 6. This is a third position. 3 minus 1 is 2, so it's 6 to power of 2. So it becomes 36, 6, and 1. And you multiply and add them, you get 177. So number 453 in base 6 numeral system is equivalent to number 177 in our numerical system. Okay. If it's base less than 8, again, it's the same thing. If you have 3615, and again, you write the digits with parentheses, it starts from here, right-hand side. First position, 1 minus 1 is 0. Any number to power of 0 is 1. this is base 8, so second position, 2 minus 1 is 1, so it's 8 to the power of 1, then 8 to the power of 2, then 8 to the power of 3. You multiply those and then do all the multiplication addition. You get 1,933. All right.
When you get to that, when you go back to that, okay, so we would start, you write the 3, 6, 1, and then 5 out.
Yeah.
Okay.
them in
And
parentheses.
then you went to the base is 8.
Yeah. And I start from
So,
right-hand side.
Okay. So how did the 1 get in here
Okay. Because
inside
remember,
the 5?
the rule is b to power of n minus 1, the base to power of its position minus 1. What is its position? 1. This is the first position, okay? Agree?
Okay. Mm-hmm.
So 1 minus 1 is 0. Any number to power
Yes.
of 0 is 1.
0 is 1.
So
Okay.
that's how I get the 1.
Okay.
Now the second one is
Okay.
second position, so n is 2, and the base is 8. So 8 to power of 2 minus 1. 2 minus 1 is 1, so it's 8 to power of 1, just 8. The third one is third position. It's 3 minus 1, 2, so it's 8 to power of 2. The fourth one is n is 4, 4 minus 1 is 3, so 8 to power of 3. Okay? So, same thing, if you have such a long, big number, 101 base 2, again, you separate the digits, put them from right to left. The first one, second, third, fourth, 5, 6. And again, remember, the position minus 1. This is 1 minus 1, 0, so it becomes 1. The second one becomes 2 minus 1 is 2. The third one, it becomes 3 minus 1 is 2, 2 to power of 2, and it goes on all the way to 6th position, which is 6 minus 1, 5, and it's 1 times 2 to power of 5. And then you multiply, you add them, you get number 45. You can see here the advantage of our numerical system, because that big number can be written in our system with 2 digits. Base 10 system, 45. Okay? Okay. That's it. Actually, we are done. But I want to show you that 2 assignment. But let's look at just these 2 cases also. Let's go to page 204. Example 3, it says convert EC7 to base 10, and it gives you a chart right next to it. So we write EC7, 7 is position 1, C is position 2, and E is position 3, and this is a base 16, base 16. So you have, again, first position, 1 minus 1 is 0, so it's 7 times 1. The second position is 2 minus 1, 1, 16 to power of 1. Third position becomes 16 to power of 2. And you do multiplication, addition, you get the number in our base system. Okay. And these are optional, but just let me take a look. Again, I will never ask you to do any kind of addition, multiplication in other numerical system. But for example, let me just mention this. On page 208, example 1, when it wants to add 33 base 4 plus 13 base 4, you can it's much, much better if you convert them to base 10 and then add them, and it's base 4 again. 33 becomes 3 times 1 and 3 times 4, and 13 becomes 3 times 4 and 3 times 3 times 1 and 1 times 4. So you add them, you get 15, and 7, you add 7 plus 15 plus 7, you get 22. But these are optional, all right? Are you guys okay? So let me show you, I want to show you that assignment. Can I have everybody, please? So I want you guys to follow. Let's just go here. Okay. This is your assignment number 3. We want to do this together. I want you to understand. The first question asks you, let me move this here. Come on. Find out which collections are well defined and are therefore and which are not. I'm sorry. Find out which collections are not well defined and therefore they are not a set. Okay. The first one, it says collection of part-time and full-time students currently enrolled at Southern California Seminary. This is a well-defined set because the elements, the members are well-defined. We are talking about part-time and full-time students at Southern California Seminary currently enrolled, okay? So this is a set. So that's not the answer because I'm asking for which collection is not well-defined, okay? The second one, the collection of elderly full-time students currently enrolled at Southern California Seminary. Well, this is not well-defined because what do you mean by elderly? At what age do you consider somebody to be old? So this cannot be a set because the terms are not properly defined. Elderly is not defined. The third question, collection of even natural numbers greater than 100. This is set. This is well defined. So the answer to the first question is number 2. The one which is not well defined. Okay, do you follow me?
Okay, you said which is not well defined.
Yeah.
So number 1 was well defined.
Yeah, because part-time, full-time, currently enrolled.
Currently, yes. Okay. Number 2 is not because they don't have a system on what defines elderly full-time students.
Yeah, what I mean, just elderly. Who's the elder? Who is the old person?
Okay. And then it says the collection of even natural numbers greater than 100.
That is well defined. So the answer is number 2. Which of these collections are not well defined is number 2.
Okay. Yes. Okay. Okay. Now I got. Okay.
Yeah. And let me do the last question. This is again one of those strange numerical systems. And again, if you notice, I always give you that corresponding number, the table. The Mayan numeration system uses 3 basic numerals to present any position. You have that oval shape, dot, and a bar. And this is arbitrary. So for the bar represent 5, the dot represent 1, and the oval shape represents 0. Okay, so they use 3 symbols above to represent number from 0 to 19, which as you can see here. So if we have this this is the number that we have. Okay, we want to see what is that in our numerical system. Remember, with the Mayan numerical system, you always start from the bottom. It's a vertical, it's a strange system. It starts from the bottom, goes up. So this one, so what is this one? Is 0. And the bar, what is a bar? Is 5. So I write 5 and 0. And it's a base 20. Remember that. It's a base 20 numerical system. The first position, remember, b to power of n minus 1. The position is first. N is 1. 1 minus 1 is 0. Any number to power of 0 is 1. That's where I get this 1 here. So it's 0 times 1. Plus the second position, so n is becoming 2. 2 minus 1 is 1. So it's base 20 number system. So it's 20 to power of 1. So it's 5 times 20 to power of 1. So 0 times 1 is 0. 5 times 20 is 100. So the answer is 100. That strange number in Mayan's numerical system is equal to number 100 in our numerical system. Following me? You follow?
So
Okay.
I have a quick.
Go ahead. Go ahead.
Okay, why is it base 20 again?
Just the, I mean, don't ask those questions. Just the way that their system, you know, we have
But
numbers.
for that one, it's base 20 though, is what I'm trying to get
Yeah. It is base 20. Remember in our textbook,
from the text. Okay.
even it talks about that. Is the first position, then the second position, then the third position, 20 times 18 to power of 2. That's just the way that they set up their system.
Okay, gotcha. That's what I was asking. Like but I get what you're saying. It's on the text. It's stating it's 20 for their numerical system. So this right here, what you're showing, that's the way we would write out the answer, basically.
Yeah.
We would leave that first section blank. We would just write it on the right side.
It doesn't matter. You can.
Okay.
Yeah, it doesn't matter. Yeah, this is fine.
Okay.
All right. Are you guys okay?
Can you go over that just one more time?
Okay.
I see the circle like is
Okay,
0.
you see, remember it's a vertical system, strange, and it goes from bottom to the top. So we have this oval shaped thing, which is 0.
Yes.
And we put this 0 on the first position.
Okay.
Then we have this bar, which is 5, based on the table. And we remember that it's the base 20 number system. So the first position, whatever basis, doesn't matter because it's b to power of n minus 1. The first position is 1 minus 1 becomes 0. Any number to power of 0 is 1. That's where I get the 1.
Okay, so you put that 1 behind the 0.
Yeah, 0 comes from that table.
That table, yes.
Represents 0. The 1 that I have there, it's a position, because remember, even our number system is a positional system. But the value of position is always, the rule is this, b to power of n minus 1. So let me get this camera. Okay, so if
you said b to the power of 1,
b to power of n minus 1. Okay, n is a position, the number of position. The position is first position, so is 1 minus 1 is 0.
Mm-hmm.
Any number to power of 0 is 1. That's
1.
where you get this 1.
Mm-hmm.
Now you come to the second position. So what is the n here? Tell me. If I'm in a second position.
The 5?
No. 5 comes from this here.
The straight line.
Yeah. But
Okay.
what's the, if the rule, remember, the rule is b to power of n minus 1. If I'm in a second position, what is n? 2. Remember, n represent the position. If I'm in a third position, n is 3. If I'm in a fourth position, n is 4. But n minus 1. So I'm in a second position, so it becomes 2 minus 1, which is 1. This is base 20, so you get 20 to power of 1, or just 20. You follow?
Yeah. Go ahead, continue.
Okay, no, that's it. I just wanted to show you these two. I'm not going to do all the questions.
No.
I just wanted to show you 2 of the questions for your assignment 3. I want you to understand it. All right?
Yeah.
Okay. So remember, you find the corresponding number for these symbols. You put them here. You add them, but you also have to multiply them by the base number depending on their position. This is position number 1. This is position 2. And the rule is this: for any base number, b base is to power n, the position number, minus 1. If I'm in the first position, is 1 minus 1. If I'm in the second position, is 2 minus 1. That's why I get 20 to power of 1. The 20 is because this system is a base 20 number. That's the way they just set it up, the way they set it up.
Yeah, so if it was base 60, we would times it times.
I'm sorry?
So if let's say, for example, it was a 60 was the base, then it would be
Then it would be, instead of 20, you will have 60.
60. Gotcha. Yeah.
Okay. Are you okay, Richard?
Yeah, I'll call you.
All right, brother. Okay, well, that's it for tonight. Brother Chad, can I ask you to pray for us?
I have one quick question before they pray.
Sure.
Are you going to be posting this recording, or do you have another?
Yeah.
Okay, cool. Just in case, I want to review it and look at the video.
Sure. Yeah, I will.
Thank you.
Okay.
I will most definitely have to refer back. Don't feel bad, Richard, because we all feel the same way. But yeah, I could close us out. Lord, thank you for today. Thank you for this class, Lord. Thank you for our instructor that takes the time to thoroughly explain things that to us is new and can be confusing. But thank you for his patience and his kindness.
Yes.
And we just we pray for everybody's remainder of the week. We just pray that you could be with us and that we could apply, that each of us could apply and take something, even if it's only one thing, Lord, from this class that we could use for your glory. We know that you are the creator of math and all things, and we just pray for you to help us understand what we need to take from this course. In Jesus' name,
Amen. God bless you. See you guys next week. Okay.
Amen.
Take care. Bye-bye.
Have a good one.
Bye-bye.